joules. We got 1 gram of coal given 7,000 calories. How many joules is this? Well, in 7,000 calories, I know that in 1 calorie, there's 4.184 joules, right? And how do I know that? Because I got into the back of the textbook and read it, right? Or if you're taking a test, I've already got it photocopied. It's back there. All right. So 7,000 times 4.184. Hit the enter button. Here's what we're going to get. 29288 joules. All right, that's the first answer to the problem. 1 gram of coal burned, going to give you this much joules. Secondly, how many grams of anthracite are required to raise the temperature of 4 liters of water? Okay. So we're going to have 4 liters of water from 20 degrees centigrade up into 100 degrees centigrade. Wants to know how many grams would be required. Well, first, why don't we calculate how much energy would be required to do such a maneuver? All right. So when we look here, here's what we've got. We've got Q equals MC, final temperature minus initial temperature. Okay. Mass of water. What is the mass of water here? No, the mass of water. 4 liters, right? It's 4,000 grams though. Because remember, the density of water is 1 gram per milliliter. So 4 liters transfers into 4,000 grams. Okay, specific heat of water, 4.184, as John said back there, joules per gram degree centigrade. The final temperature of that water is 100, so it's boiling, right? Minus the initial temperature at 20. So this answer right here is how much heat, not how many grams of coal. See, chemistry's got to work in steps. How much heat would be required for this maneuver? All right, so 4,000 times 4.184 times 100 minus 20, close the quantity. That's going to be 133,880 joules. Okay. So that would require 1,000,000 joules of energy to crank this temperature up. Now, what are we doing? Well, here's what I know. I know that in 1 gram of coal, 1 little gram, how much energy does that produce? 29,288 joules, right? Well, I want to know how many grams, who knows, will produce a whopping 133,880 joules. So what are we going to do? Just cross multiply, right? Divide it however you want to talk about it. So that number times 1 divided by 29288. So we should be getting 45.7 grams of coal to get this much energy. Right? So if you're working for some sort of an electrical company or whatever, I mean, naturally you need to know how much coal to order, right? Now, some of that obviously is an approximation because who knows how cold it's really going to get and how hot it's really going to get. But a lot of times when you are ordering chemicals, it's okay to approximate, about what you kind of need, right? Like the one guy I worked for or worked with, you needed like 300 milliliters of chemicals a year. This much chemical a year. He would order 4 cases on special. The chemical would go bad before you even thought. I mean, that chemical would last 25 to 30 years. Why would he store all that up? I don't know. I mean, it's silly. So, anyway. Okay, what else have we got? This has been Chapter 4. That's wonderful. What a great review for the test tomorrow. But you got something else for me?
Yep.
All right.
This is chapter 2,
Chapter 2.
and it's a temperature question. It's number 46D. It's 100 Kelvin to Fahrenheit.
100 Kelvin to Fahrenheit. All right.
I know, you don't get
Check out that clock. 100 Kelvin to degree Fahrenheit. Isn't that clock neat?
What number are we doing?
I don't know. 46D. This is Chapter 2, number 46, Part D. So I suppose if a little guy like comes out of the wall or something, we have ourselves a horror movie, right? Chemistry in the dark. Okay, well the first thing we got to do is get degrees centigrade. Okay, so here's what we got. I know that a degree centigrade temperature plus 273.15 equals the Kelvin. Okay, so 273.15 equals 100 degrees centigrade. So what is that? Well, 100, wait a minute. 100 minus 273.15 would be negative 173.15 degrees centigrade, which would certainly be cold, right? I mean, 100 Kelvin's pretty cold, right? Alrighty, now what have we got here? We've got 1.8 degrees centigrade plus 32 equals my degree Fahrenheit temperature. Okay, so 1.8 times negative 173.15 plus 32 equals whatever that is in degree Fahrenheit. Now, remember we got an orders of operation thing happening here, so we're going to multiply first, hit the enter button, then do the addition, right? Okay, 1.8 times a negative 173.15 equals plus 32. So that's going to be negative 279.67 degree Fahrenheit. Final answer. Okay?
We got that answer in the book. The book says negative 300.
Negative 300. Do you know why they said that? They're doing significant figures. This number here has 1 sig fig, which means your answer needs 1 sig fig. So that's why the book says negative 300. Yes.
What is that next to 1.8? Is that an upside down A? I don't know what that is.
Oh, that's an asterisk. It's a star.
Okay.
It means multiply. I'm glad you're asking. I don't care.
How'd you get the minus 173.15?
Oh, here. I subtracted 273.15 here. And subtracted 273.15 here.
Oh, okay.
So 100 minus that. 32. Chapter 2? Okay, so here's what we got. Oh, yes, sir. So professional. All right, so number 32 is we're going to have 133 miles per hour to centimeters per second. All right. 133 miles per hour to centimeters per second. All right, well, first thing is, as far as our units go, we're going to have a miles per hour going to a centimeters per second. So we've got two things going on.